recording because I forgot, but now we're recording. So it is what it is. And now we can go back to the big diagonal member. Where here we'll have AYAX, we'll have BYBX, and CYCX. With their heights being 4 feet, 8 feet, well, 4 feet, and from here to here, 4 feet, whole thing 8 feet, and 3 feet, 3 feet. So then A still has both unknowns. At B, we have both B values. So I'm just going to mark these as found. These are unknown still. And CX is found. So now that we've gotten rid of B, we have them as knowns, and we only have CY and our A values, we can do moment at A. Moment at A would get rid of both of these as they pass through A, and this will be our only unknown. So this is why I say the order is kind of important, but not really, because you're going to have to do all the members anyways most of the time. Right. So it's not like you look at this and it's like, oh, you only have to do this member right here and you can ignore the rest of it. You're going to have to go through all of these drawings regardless. So we have this equation, only unknown CY. So we can say the sum of the moments at A, once again, so that we can get these to cross off, equal to 0 is going to be equal to our BY, which we found to be 300 pounds going down. And that was on this member. So our BY on this member, it's corresponding like other side of the pin, the direction is going to be up. Because here we found it as 300 going down. And I'll change the drawing a little bit so that it reflects this. So we found BY equals 300 here. And that was on this member right here. So on the other side of this pin, here on this member, BY has to be going up. So BY is going to be like this, 300. And so we can say the same thing for BX. BX we found to be going to the right. So BX on this member has to go left. There we go. And so BX was 525. CX on this member we found to be going to the left. So on this member, it has to go to the right, opposite side of the pin. So we'll have 75 pounds here. £75. These are not important because we're getting rid of them. And CY is the only thing left. So you do your moment equation with these values at those distances. So this would be moments equals 0. That'll be minus 300 because we're going to go like this, assuming clockwise is positive. So this is going to move against that. So we'll have minus 300 times the distance to there, which is 3 feet. We know that because it's half of this. Then we'll have minus 525 because this is also going to move against the direction. As this moves this way, this is going to move the opposite way. Minus 525. Here to here is 4 feet. We know that from here. Then we'll have plus 75 because this is going to move this way, same direction as the moment. Times the total height of 8 feet. And then finally, we will have minus cy, because we're assuming up, times the total length, because this is going to move like this. So this is going to be the entire 6 feet. So from that, we can say that cy is equal to
I thought for moments for like cy, you had to find the perpendicular distance.
you do. So this
Okay.
distance is the 6 feet because cy moves up and down. So we'll go down this dotted line to the shortest distance, which is the perpendicular.
Okay.
That's why for cx, we say this, and we go along this perpendicular. And that's why we use 8 feet for cx.
For cx, is that minus? That's minus? 7
This is plus.
okay.
Yeah, it's a little hard to
Yeah,
see. There. Yeah, so we can say that cy is 75 pounds. And that's according to the solution, that it moves on this member down. But the question wants the C components on this member. So we will say, just like how we said Cx is equal to 75 pounds to the left on CEF, we will say Cy is equal to 75 pounds up on CEF. This is up because we found down on here. So the opposite side of this pin is this member, the one we care about, so its direction is reversed. Oh wait, sorry, I misread. That's supposed to be 100. I accidentally read CX instead of CY, but this is correct. That's correct. It's just 100. And the direction is correct. And that's how you would find CX and CY that this member exerts on this member. So any questions on this problem or this concept?
Can you go real quick why, like, on the opposite side, like why you have to do that? The opposite side is the opposite direction.
Yeah. So the idea, I'm just going to erase this diagram here. And let's look at something. Let's just say we have something with two pieces like this, right? And let's say we have a pin right here. And this is like a support. And this has like some random force on it. So this concept, you remove this pin, and then you basically say that this becomes this plus this. It's just two different, like you break it into two pieces. So the forces that you find here, when you do this, have to be reflected here, that same point in an opposite direction, because when you look at this, there's nothing here. So that's why if you get like this, let's say this comes out to be 50 for some reason going up, based on whatever force and distance you have. That 50 is reflected like that by going down, because this is the reaction here that the force exerts on the structure. And so that 50 gets transferred into like the rest of it going down. Yeah, that's how it works. Any questions in the Zoom? Otherwise, we can move on to a different section.
So first you did CEF.
Yes. So we did this first, and then to find EX and CX. CX is the first part of our answer, and we get that pretty quickly. But we need EX because later in the problem, when we have to look at this beam, we're going to need that value.
Right. Okay. So you took the moment at C
Yes, we took the moment at C here
to find EX.
to find EX.
And then you took the moment at F.
No, we just did some of the forces in the X.
Sorry. Okay.
Right,
Okay.
to find CX.
And then how did you find CY?
So CY we found all the way at the end of the problem. It was the last thing we found. This diagram, you can't use it to find CY because if you look in the Y direction, we have 1, 2, 3 unknowns. That's bad. So we went here to this pulley and we found dx and dy, and we did that so that we can go here and have those values known here. We have ex known, and we have unknowns at b. So I had a diagram for it here. It showed this member with all the pins separated, and we used that to get these equations, which let us solve for EY and BY and BX. Once we had those, we could go to this big member here, and we had both our B values known and our CX value known. CY is unknown and A values are unknown. So we can do moment about at this point, and CY becomes our only unknown. We can solve for it that way. So you have to start here, figure out what you need to find, get what you can, and then just work your way through the structure all the way back to this point with everything you find. No problem. Okay, so that was a frames problem. So we can do an internal forces problem. And let's just go with the most complicated thing I can find. So how about problem 3 from internal forces 2? So I'm just going to write that here. PR3 from internal forces 2. So here we'll have a wall with the beam coming out from it. This is A. So this is going to have AY, AX. No, I don't think you guys did this problem in class today.
Right. It was similar, but yeah.
Yeah, you guys did an internal forces problem today, but not this one specifically. So we have the moment here on the problem. That is 350 foot-pounds.
Would that mean the moment at C equals that? Or
So
when I see that symbol, you're telling me that
This-
that equals 360?
yeah, so this is an applied moment on the member.
Oh, so it's just-
Yeah, so this is not like at a point. It's not at A. My bad. I should have clarified. There's like a
Because I noticed that they would be, I would see that and I would be confused, like, is that a particular point or is that?
okay.
a reaction?
No, so this is an applied moment 2 feet away from A. So one of the biggest things for recognizing whether or not a moment is like given at A or if it's on the member, if it's weird to tell, it will usually tell you some kind of distance here. And so this problem in the dimensions along the bottom has a distance of 2 feet from A to this point. So you can infer that the moment is applied and not a reaction. EY, 1 foot. B is 2 feet.
This equals this.
80 pounds per foot.
And then since it's above 0.005, this would have to be lower than this number. Like if you're yes.
Yeah. Oh,
That's why we're going over it.
So it's just like it's the same. So equals the maximum.
Okay. So this is the whole thing. And what it is we have this entire structure, these multiple members that are pinned and attached to each other in between this wall and this wall. And the question wants us to determine the normal force, the shear force, and the moment at the sections passing through points E and F. So here and here. Member BC is pinned at B, and there's a smooth slot in it at C. The pin at C is fixed to member CD. So basically, it's saying that here's a pin attached to this, and then there's a pin on this member that this kind of sits onto. Let me know if you do you have this all written down?
Yeah. Okay.
Okay, cool. So to start this,
What is a speed slot?
so a smooth slot is, it's just like, there's a pin, but the hole on one of the members is like way bigger. And so this could, if it wanted to, slide this way. Yeah, so that's all that means.
So the difference between E and B, just looking at the drawing, E is a moment or a fixed moment, and then B is a pin.
So E, yeah, B is a pin that you can pull out and separate this from that. E is just a point here. It's just a point because the problem is asking us to find the normal shear and moment at E and F, and it's just labeling them as E and F. We don't have any information about them yet. This moment is applied 1 foot left of E and 2 feet to the right of A. So this is just kind of here. It's not associated with A or E. So we can start by breaking this up into its pieces, which are going to be from here to here, here to here, and here to here. So let's start with A to B. So this is going to be our A to B section. A is here, E is somewhere like here, and B is here. We have the moment of 350, and these are the spacings for them. We have our AX, AY. And we have MA. All at A, we have the applied moment, and we have BY, BX, because this is a pin. So we'll say BX and BY. But the question cares about this point. We can go ahead and draw the diagrams for all of these. So we can say that BC is this, B and C, with distributed load, 3 feet from B, and a value of 80 pounds per foot. And we have another force with 60 degrees here, and this value is 500. All this just being taken directly from here. So then we can say our BX and BY. So I will assume BX and BY, why not? And here at C, we are only going to have CY. And this is why it's important that it's a smooth, whatever it's called. I don't remember what the problem is. Smooth slot, thank you. Because there's no CX here, because this can, if it wants to, move in the X or Y. It's not going to, because this is a fixed wall and this is a fixed wall, but because of this smooth slot, we don't have CX here. Anytime there could be movement, and that's why rollers and smooth slots don't have the X component, the component that that kind of structure allows for. And then finally, we have the last section here as C FD with dx dy moment d and cy. So now right here, I'm just drawing them arbitrarily. The cy's are both going up. They will not both go the same direction though. Going back to what we said about the pins, one of them will be up, one of them will be down.
So even if it's completely horizontal like that, it'd still be opposite.
Yep.
Then how come you're writing moment about A and moment about C on sides?
Because this is a wall right here, and this is also a wall right here. So anytime you have the not just like a fixed support, but if it's fully attached to a wall, it has a moment.
Okay.
To leave, I'm sorry. Oh, okay. So nobody in Zoom, but that's all right. I will be less concerned about the computer. I'm still going to try to keep it on the board because, you know, I'll try to put this, and I figured out, so my LA page has been down because I just didn't realize it wasn't published. And so I figured out how to publish it, but I just haven't been able to sit down and actually do it yet.
Yeah.
So I'll be able to do that sometime this weekend before the quiz. So this video will be back up for you guys to watch.
Okay, so we have to go on your Canvas page.
Yeah, so I will have a section in the modules. I I will have a section in the modules where you guys can find like everything that I do. And up until this point, it hasn't been able, like you guys haven't been able to see it because I didn't realize when I first made it that you guys couldn't see it. Yeah.
Okay.
So we have all of our pieces now. We can start doing equation stuff.
So this will get you started. If you approach a problem, do this.
Yeah, if you have something like this, break it up, see what you have, and you can go from there. Oh no. Hello? Marker? No. Come on, write something, please. This has also been on my to-do list to get markers. Yeah. You guys don't happen to have a marker. Dang it. If not, I will probably actually just run to a classroom and borrow one real quick, but like. All right, I will be right back. Yeah. Yeah, whatever color you got. Thanks, bro. This is also yours, actually. Okay, so now things are written in green.
So you're gonna post this video, right?
Yes.
Well, it's okay. Yeah, I told my girls, like, you guys gotta double check the work. But,
Need some extra credit.
I tried, man, and he was like, yeah, which I get why he's saying that, but
I can't post those students.
would be cool though. More people would show up. Mm-hmm. So we have our three pieces, and we can.
no, just come.
So we can start with BC to get these values, because we can take the moment at B and solve for CY. We can do some of the force in Y direction, get BY after that, etc. So the first thing we can do, like I just said, we can do. Oh, this is way better.
I think we got it right.
We're gonna do some of the moments at B. It's gonna be equal to 0. So these are gonna go away. So this distributed load of 80 pounds per foot is gonna be over 3 feet. So that's 240.
Okay, real quick, sorry. How come we're starting with the second piece first?
Okay, so this is kind of what I said earlier of like the order you start is not as important as just like having everything and going through it all. Because no matter where you start, you're gonna have unknowns. Like if we start here, there's gonna be a bunch of stuff we can't solve for. It's like, okay, let's try something else, right? We'll go here, there will be stuff we can't solve for. Okay, let's try something else. So we have the most information here, so we can start here.
Okay.
And it will allow us to actually get the ball rolling. So this member will have moment at B. We're solving for CY here. So in order to do that, we'll do the 80 pounds per foot over 3 feet times the distance, which is going to be, since this is a triangle, it's going to be 2/3 from here, like that way, because it's more heavily weighted. C is like in a regular distributed load like this, where it's a square. Yeah. So let's say this is 10, right? Like 10 pounds per foot. Normally, in order to get your point load, like to make your distributed load a point load, you would take your entire load, multiply by the distance x, and then the distance to your point load is 1/2 x, because your point load is going to be in the middle since it's a square.
Right.
So in a slanted or triangular distributed load like this, where it looks like this, we still multiply by our entire distance x to get the point load itself, but its location is different because we can see that the load changes as you move. So the load on the triangle is going to be 2/3 into the triangle, or you can say 1/3 from the big side.
Okay.
So your point load is going to be closer to the big side than it is to the little side.
So 2/3 closer.
Yeah, so 2/3 this way.
So how would you? Okay. So just 2/3 of 3 feet or
Yes.
800.
Mm-hmm. So well, we have 80 pounds per foot over the whole distance under it, which is 3 feet. So that makes our point load value 240. But the distance to the point load is 2/3 of this 3 feet. So the distance is 2 feet. The point load is going to be somewhere like this.
Okay.
So we can say 240 pounds, 80 times 3, times 2 feet, because that's the distance to this point load. And then we have this force right here, the 500 going at an angle. And if at any point I'm going too fast, just say so and I can go slower.
Real quick.
Yeah.
To the distributed load. I just want to kind of write out the formula.
Absolutely.
I already went through distributed loads. But so it'd be 80 times 3, and then you divide by that.
Yeah, so you do the force still divided by the total length that you have.
Okay. Oh, so 80 divided by 3.
Or I mean multiplied by 3. Sorry.
Right. And then you get that 240.
Mm-hmm.
Right, and then you multiply it by 2/3 of the distance there.
Yes, because the way it works, right? That's exactly correct. We have the distributed load, so we have to make the distributed load a point load by multiplying by the distance. So this distributed load that we have here, like it's going to be, we'll still say that it's 80, right? It's 80 pounds per foot. So when we multiply by our distance of 3 feet, this turns into this.
Okay, I got it. Yeah.
And so then the distance that we need, because we are taking a moment, we're taking a moment at this point. So the distance from here to there is 2/3 the distance we used. And you have to make sure that you go into the triangle. If the triangle was shaped this way, if the triangle was shaped like that, and the moment we were taking right here, it would only be 1/3.
Okay.
Because it's all relative to where the peak of your distributed load is.
Okay.
Does that make sense?
Right. So the distance from where that point load would be at would be 2 feet, and then it's going to be multiplied again.
Exactly.
Okay.
So yeah, that's how the distributed load works when it's not uniform.
Right.
So these are considered uniform. These are not.
Okay, so you're always trying to pretty much find point load if it's on a course like that.
Yes. Anytime you have a distributed load, whether it's like a square or a triangle or whatever shape he gives you, he should only give you square or triangle.
Yeah.
I would be shocked if there was another shape. Yeah, exactly. So no matter what, you want to multiply by the entire distance that you have. And then you multiply by if you're doing the moment, you still need the distance from the point you're taking the moment at all the way up to where the force is at. So that's where 240 times 2 feet comes from. So the next piece is the 500 pounds right here. So this is also going to have to get broken up into its components because it makes it easier to work with like that. You could technically do the 500 and find the distance from like here to like this, but like, no, don't do that. That's like a way more effort than you need to like do for this. So we have the 500 and we want to make it X and Y. So the X component, spoiler alert, looks like this.
Right.
So that goes away. It's going to go through B, so we don't care about it. This is going to be the X component right here.
Okay.
The Y component is going to look something like this. We can say that this is moving left and this is moving down because this arrow is moving down and to the left. So its components do the same thing.
Okay.
Then we know that BX is going to go away because we can look at the point that the load is being applied on right here, and we can do the components at that point, going into that point. So that's how we know that BX, or that the X component of 500 is not like up here for some reason.
Right.
You always want to make your components at the point that the original load is on.
Okay, so like 500 cosine 30.
Yes.
In the Y direction.
Well, 500 cosine, 500 cosine 30 will give you this, exactly.
That's what we get about X, right?
Exactly. So you can do that as 500 cosine 30 or sine 60. Both ways give you the same.
Okay, I just thinking 30 is a Y direction, but
Right. Yeah, because this is 30 and then that one's 60. It doesn't matter. It's just know that both ways work so that you have multiple options and you can never like find yourself stuck that way.
Yeah.
So we'll have if we're going clockwise around B, this is going to be with that direction. So we're going to say plus 500 pounds times the distance, times cosine of 30 times the distance from B to that component, which is just going to be our 3 feet. And then last but not least, we have CY, and this is going to be minus CY because we assumed up, which it would be against our moment. And then the whole distance from B to C is 3 plus 2, 5 feet. So that lets us say that CY is equal to whatever that is.
you already have the solution on there?
I do, but it's if you want to do it. I made one mistake. I made one mistake in that when we have a distributed load like this, since it's a triangle, we don't just multiply by the length, we also have to multiply by 1/2 because we're missing this whole piece of it.
Yeah.
So whereas this would just be the distributed load value times the length, and get the area, because what you're doing is you're getting the area of all of this. When we do the area, we're missing this piece, so we have to do 1/2.
Okay.
So this is going to be 240 times 2 feet times 1/2. So it's just 240 times 1, basically. Because you can think about this as like this is just the area of a rectangle. So base, this value, times your height, which is your force value.
Yeah.
Triangle is 1/2 base times height. Height being your force value, base being your distance.
Okay.
How did hydraulics go?
Hmm?
Hydraulics, how did it go?
Oh, thanks for asking. I think it went pretty well, actually. Yeah. There was one question that was like way harder than all the other questions, but I think that was probably just because I didn't know that section as well as I did the other sections. So, but I feel like I did pretty good. Yeah.
It's good. It was only one question that you did well.
Yeah, I think so too. 112,000. Wow. Holy crap. So, did you do? So I guess first check your calculator inputs.
Yeah. So I did 500 times cosine 30
Times 3.
plus 240, right?
Mm-hmm.
So that's by 5, 307, going to 81.
And that is exactly what we're looking for. 307.8 pounds. And that is going to be a positive value. So we know that our CY direction of up was correct. So we have our first thing solved for. And now we can do some of the forces in the Y direction and get BY. So do you want me to go through some of the forces?
No, it's okay. Just that I know that we're supposed to solve the forces in the Y direction.
Okay, so I'll just say some of the forces in Y equals 0 gets you that BY will be equal to, oh geez, excuse me, 245.2.
So you'd be doing cosine 30 for this one, or 500 times cosine 30, right?
Yes, you would do cosine, or you would do cosine 60. Oh wait, no, for Y direction, yeah. I'm like misheard what you said. Don't worry. But yeah, so some of the forces in Y direction, we would have BY is unknown, CY we just found. We would have our distributed load. So it would be the 240, the 80 times the distance, and we don't need the 2 feet because we don't need the distance from the point to the point load. But we still need the times 1/2. So it would be 80 times 3 times 1/2.
Okay.
And then for the 500, it would be 500 cosine 30 or sine 60. We drop the 3 feet because we don't need this distance. That's how we would get BY. And then we would do some of the forces in the X direction equal to 0. And that would get us that BX, if we say BX minus 500 cosine 60, then that's everything for the X direction. So we would just say that BX is equal to 250 to the right. And for all of these, it's important to write on BC. And this distinction basically tells the professor or whoever's grading that you know that these values are this direction on this member specifically, leading back into when we go to this member, CY is going to be down.
All right, that makes more sense.
Mm-hmm. So now that we've solved everything here, we can move and start finding our values at E and F like the problem wants. So do you want to do E or F first?
Do F first.
Okay. So I'm going to go ahead and erase some stuff just to clear up a little bit of space. So starting to find F, we would know that we need to take a cut at F. So we would basically do something like this, and we would say that our new thing goes from C to this point, F, where we have a shear value, a normal value, and a moment. And here we have CY. I'm drawing it down because we've already proven that it will go down on this side.
Okay. So what's that on the F a little bit there again?
So we have the shear force, the normal force, and the moment. And these are the three values at F that we're asked to find. So now that we have CY, and this is why we started here, because now that we have CY, these equations are very straightforward. So we can do some of the forces in the Y direction. That would just be minus CY, and I wrote it down, so we would say minus F shear. That would get us that F shear is actually going up, and it's just the same value as CY. I can write it out as some of the forces in the Y direction equal to 0. It's going to be equal to minus 308 pounds minus F shear. And so you would just add 1 over, and it's equal to minus this. So then we can just say that the F shearing value is equal to 308 pounds going down.
On just that CF cut.
We're going up. Because we found CY to be going down, and I wrote this as going down. And if we get a negative answer, this one has to be the opposite direction I assumed.
Okay. Oh, yeah.
So that's how you get the F shear. You would then do some of the forces in the X. F normal is going to be the only thing here. So it's going to be equal to 0.
Okay. So, all right. Well, the X normal force is just that one CY force going down, or is that the force coming in from the right, like at F?
So this one here is the normal force. So when we want to find that one, we would do the X direct, some of the forces in the X direction. And this is going to be the only thing there, so we know it's equal to 0. So that's how I'm going to write Fn. Fn is equal to 0. And last but not least, the moment here. So I'm just going to write this as this Fs, Fn, and Fm. The shear, the normal, and the moment. So when we do the moment, we would do it about F, and we would have some of the forces, some of the moment. We can do clockwise. Moment. Damn, I cannot write how I want it to write. So here, it's going to be clockwise positive, sum of the moments at F, there we go, equal to 0. So that's going to be, let's look at this first. I said clockwise positive, and here I assumed the counterclockwise, so we're gonna have minus FM. I'm just saying this is the moment at F. Yes. All right, no problem then. I'll see you later. So then after this, we have CY. And I said clockwise positive, so that's going to move against the clockwise direction. So we'll have minus CY times the distance from C to F, which is 4 feet. CY is already known. We found that here. So I'm gonna write this as MF instead of FM. Moment at F. There we go. So that what'd you forget? That's important. I said that's important.
Yeah.
So you would have this times 4, which is 1231.
1,231.
So 1231, and we get this once we add it over is positive, but this is negative. So the direction that we assumed is going to be opposite. So this is going to be foot-pounds in the clockwise direction. And that is exact. I have to sneeze. Thank you. I know.
Okay, so we just found the moment that we found was negative, so that just changes the
Mhm.
west position. Okay.
Yeah, I assumed counterclockwise. We found negative, so I wrote clockwise. And
I thought right there we were seeing clockwise.
so this is counterclockwise.
Yeah, but when you actually started the equation.
No, when it's so here I assumed that clockwise is positive,
Oh, okay.
but the moment I wrote as counterclockwise.
Oh, okay.
So I said clockwise is positive, so our moment is counterclockwise, so that's why I wrote negative here.
Okay.
Then this goes against our clockwise positivity,
Mhm.
so that's why this is also negative.
Okay.
We get this is a negative answer, so I changed the direction to clockwise.
Okay.
So this one, even though it looks like super complicated, like there's so much going on, this is actually the entire set of answers for F already.
Yeah. Oh, and that's what we're trying to.
Yeah, now all we need to do is do E. So we'll go over to this section and we'll be like, all right, taking a cut there. So the actual diagram that we're working with looks more like this, where we have our BY and BX at B, then we have E with the shear, the normal, and the moment, and everything on the left can just go away.
Okay. How come?
Because we took the cut here and we're choosing to look at it from this side.
Okay. Since we don't need.
Since, right. So even this applied moment here actually doesn't matter because it's left of E and we already have everything we need on the right side.
Right. Okay.
So we can start off with, we found both of these values, BY and BX here.
Right.
So we can start off by saying some of the forces in Y direction. It's going to be equal to, I'm going to say, yeah, shearing is V. So
this is opposite, right? So we got 245.2 going up.
Yes,
For here, we're gonna have it going down, right?
correct. So by was up, so we know that it is down here. And bx, we got to the right, so we know it's going left. So for some of the forces in the y direction, we're going to have, I wrote it down, so we'll have minus the shear at v, or shear at e.
Oh, okay.
There's so many letters.
So that's what that V equals?
Yeah, so v is shearing. I should have wrote it like this in the first part, but
That's okay.
yeah, so v is shearing, n is normal force, and m is moment.
Okay. Right. Oh, okay. Okay.
There.
Okay.
And so just looking at this diagram, we have the shearing at E. I wrote it going down. We're going to have minus by. So that's minus 245.2. So this is just going to be 245.2 going the opposite direction we assumed.
Okay.
This is pounds going up. Because this comes out to be a negative value. We have minus and minus.
Okay.
So that's why the direction flips.
I know that gets confusing because we assumed when we started it, it was going up, but originally assumed is what we're going off of, right?
We assumed when we started this that VE was down.
Oh, I forgot. Okay.
Yeah, so this right here is VE.
Mm-hmm. V.
That's VE.
Yeah.
So we'll have VE, NE, and ME. And then we can do X direction. We're going to have plus NE, because I assumed to the right, and minus BX, which was found here. So then we just say that NE is equal to this. 250, we get a positive answer. So our assumption that it was moving to the right is correct. There we go.
Okay.
So last thing is the moment here. And we can do clockwise positive moment at E. It's going to be equal to ME. And then the normal and shear are going to go away. BX is going to go away, and we're just going to have BY.
Normal and shear go away because it's on the x-axis normal, and then y on the count force, and just bx and dy, or bx and then count force, just dy.
Yes. So BY is going down, going with the direction we assumed. So we'll have plus our BY value of 245.2 pounds times the distance to that point, which is just going to be the distance from E to B, so 2 feet. So ME, we get a negative value of 490.4. We get a negative value, so our assumed direction of clockwise is incorrect. So this is foot-pounds going counterclockwise. And with these three diagrams, starting with where we have the most knowns and the least amount of unknowns, we can solve and move to the side, find your shear, normal, and moment for both E and F.
Okay.
Any questions?
Why did we need to make this cut for these?
Oh, so we had to make a cut because this specific question says, determine the normal force, shear force, and moment at sections passing through points E and F. So points E and F are not pins.
Okay.
They're just arbitrary points that they label on the diagram where we're going to make the cut. Because you can only find the normal shear and moment by making the cut at the point that you want.
Okay.
So we make the cut here to get this. As soon as we make the cut, this piece becomes this, and we can say there's a moment, a normal, and a shear right here. Same thing for F. We make the cut here, and we take this left piece, and we turn it into this, and where F was, we have the shear, the normal, and the moment.
Okay.
Yeah, no worries.
Okay. Makes sense.
All right, so that was internal forces. We got cables and pulleys. Any preference?
Just probably the most difficult one.
So we can do cables first and then pulleys.
Okay.
So this will be problem 4 from lesson 21, cables. So
is cables similar to distributed loads?
yes, because in a cable, you're really only going to have like a distributed. Well, you could have a point load on the cable, but
Okay.
I think for the most part across the cable, you will have a load for this class.
So cables will be a little bit easier.
I think that cables are not that hard.
I've been kind of the mechanics have been slacking a little. Well, just watching like the review lectures because I have a physics 2 exam this Tuesday, and like I just been trying to study everything in that class. It's,
Mm-hmm.
it's like chapters 5 through 14, midterm, he doesn't have any other exams, so.
Yeah, I feel you on physics. That class is a lot of work.
And he's like so afraid of people cheating now, and he's like, no paper in front of you.
No snap.
So I don't know if that means that the exam will be easier or what, but I'm just studying everything.
Yeah, dang. Well, good luck with that, man. So for this, we're asked to find the maximum tension in the cable where it occurs and the minimum tension in the cable and where it occurs. And one of the questions is how long is the cable, but that's labeled in the diagram. So, oh wait, no. The horizontal length is given as 75 feet, but the cable slacks. Yeah, I misunderstood. So we're looking for max tension, min tension, and length of the cable.
Does it matter where the arrows are coming down at or anything like that? Or is it all just kind of distributed load?
So it's all just distributed load. As whenever you see like a whole bunch of arrows moving in the same direction and they're all connected by you can see in this picture it's a base on the tip of the arrows, and many other questions when you have just a member like this, the connection will be at the top and the arrows will come down.
Yeah.
But no matter, as long as they're connected, it's a distributed load.
Okay.
So for this, I believe we have a couple formulas. We have, sorry, I should finish labeling this. This is 100 pounds per foot. So we have T max is equal to W naught, which is our load, times L over 2 times the square root of 1 plus L over 4H squared. So you guys get equation sheets for your quizzes, right?
No, but it's open notes in the book.
Oh, okay. Oh, it's online?
Yeah.
Okay, I still have it in my head that you guys go in for quizzes and stuff.
You
Yeah.
have open note, but it was in person.
Oh, okay.
What did you have that? Whenever you were doing?
No,
Oh, it was not.
no. We got an equation sheet, but it was not open note. At least when I took the class. So this is going to be important. Really, this picture that we have just kind of has everything we need in it.
Right.
So T max, as long as you have this equation, it's going to be equal to your load, which is 100 times the length, which is 75 over 2 times the square root of 1 plus 75 over 4 times this, which is just how much the cable sags beneath the perfectly horizontal line between these 2 points. So that's what H is. This is equal to H. So that's 4. And this gives us T max.
H is how much it sags?
Yes.
That's weird. So I guess it gives us H.
Yes.
Oh,
So
okay.
H is here.
I was confused about the 2 4 thing. That's 4 times.
Oh, yeah. It's 4H. So
Okay.
So throw this in your calculator, and that's T max.
And that's all we're really trying. Oh, maximum pitch.
Yep.
Uh, 1,572.42.
Double check that. T max is supposed to come out to 17,000.
Okay.
Did you? I didn't write it here. There's a squared on L over 4H. Yeah, I say it every time I have a review section or a session. I tell everybody, never be afraid to double check your calculator work.
Yeah. Okay. I got the right answer.
Okay. So it comes out to 17,970 pounds, which is 17.97 kips. And that's the first part answered already. So then T min is equal to this equation, W naught times L squared over 8H. Once again, we just kind of throw in what we know. W naught is 100. L is 75. We cannot forget this squared on the L. And then 8 times, I wrote H again, but it should be 4. There we go.
I got 70,578.
That is correct. 17.58 kips.
So pounds per feet, you have to move it over 3 places to get kips.
So the answers will for these values will come out in just pounds, not pounds per foot. But yeah, a kip is 1,000 pounds.
Okay.
So then we have one last equation to find your L total value, which is the length along the cable. So not from here to here. The length we're looking for is from here along this cable like this. So we have to include all of the sag distance. So we have L over 2 times 1 plus, this is a 1. 1 plus 4H over L. This quantity squared plus L over 4H. And then times the inverse sine of H. Where's this? Or is that sine hyperbolic? Okay, so here I'm going to ask you a question. Have you seen these equations before?
I haven't, but I have probably looked that down for on the equation sheet.
Okay.
We pull up the equation sheet.
If you have it on hand, yes. Because I have one question about whether this is inverse sine of h or hyperbolic sine. And I don't know if that's something you've ever heard of or not.
Okay, uniform distributed for horizontal loads. So L total is L over 2. Yeah, radical 1 plus 4h over L squared plus L over 4h sine h inverse.
H inverse.
Yeah, and then times 4h over L.
Okay, yeah, I just want to see like it more clearly written. Okay, so I'm going to need to check something real quick to make sure that I do not mess this up for you guys.
I should probably print this out.
Yeah, so it is the way that I thought it was. So it's not, I should say it's the way I thought it was after I wrote it incorrectly. So this is sine h minus 1 of this quantity 4h over L.
So does it matter the way you, because you wrote it, like I wrote it inverse sine times h.
Right, so this h is not h. This is hyperbolic sine.
I'm not even sure now how to put that in.
I think your calculator should have like a way to just do it.
I guess the
But
quiz only covers internal forces and cables. Quiz only covers internal forces and cables.
Oh, does it?
Yeah, they just emailed us.
Oh, well, okay. Well, this is a cable, so no pulleys and no, what was the other thing that no frames?
Yeah, I guess not.
Okay.
Yeah. Cover the following internal forces and cables. 0 and 4, yeah.
Okay, so only internal forces and cables. So we don't have to go over pulleys after this then. But we do need to figure out hyperbolic sine. Because admittedly, this is not something I remember.
like math.
Yeah, it's in some weird section. I'm looking up how to input it because I haven't had to do that in a while.
Yeah, I was gonna say, because I mean, he only gives us like 40 minutes to do it.
Mm-hmm.
So I was like, no way to give us frame probably.
Yeah, that makes sense actually. That makes sense. So you'll probably have one internal forces and one cable. The cable problem shouldn't be much different from this. So as long as you have your equations here, and then once we figure out this, like you'll have this equation, then that will be all there is to it, basically. Holy crap. That's where it is. Okay, so I'm going to show this on the Zoom too, so that way this will be in the recording. So on your calculator, if you hit second, and then down here there's a button that says catalog in yellow. It's right above the actual button. It brings you to the menu that looks like this. You will then hit LN, which brings you down to the section that says 2 sample F test, 2 sample I test, 2 sample T interval, etc. It's a bunch of statistics stuff. So then if you scroll down, there will be eventually, if you keep scrolling down just a bit into the S section, you'll see sine, inverse sine, sine H, and sine H inverse. And that is where you will find sine H inverse. Yeah, so I don't know if he's told the class that in lecture or anything, but yeah, that will be very important. And I'll probably send an email out about that just so that people know where to find that in their calculator. So I'm actually going to write that up here so I don't forget. Sine H inverse 1. That's where that comes from. So using this formula and plugging in what we know, L is 75, H is 4. That's the whole thing. It's just a bunch of stuff using L and H over and over again. So the total is going to be equal to 75.6 feet if you do all this out. Once again, you have to find this in your calculator by doing second catalog, hitting LN to get the list to automatically move down. You scroll down until you find the sign function you want. And the one that we want is inverse hyperbolic sine. And that's pulleys, or not pulleys, cables. I'll look in another cable section or cable problem real quick just to make sure there's nothing else to it. But I picked the one of the later examples, so it should be pretty set in terms of having everything. Oh, this one has way more on it. But in this one, you're just treating them as though they're members by leaving them straight. So it's essentially, it's more like a trust question than like what we just did. So we can go over that as well. So these are the easy easy cable questions where you just follow the formulas to get the numbers that you want. Any questions about this before I erase it?
No.
Okay.
I'm just making sure I can do that.
Yeah, of course. So we're going to do problem 3, lesson, whatever lesson cables is, 21.
What was the final answer for that last one?
For the length, 75.6.
Okay. Keep going through this.
You can, if you want, I can look at what you put in the calculator.
Well, I just kind of did everything like one by one. So like the 4.4 over 75, I got 0.0455 sine h. Yeah. Well, I'll do
4.4. I think.
I did 16 over 70.
Okay. I was gonna say that should be 4 times 4.
I'll ask you after you go through this one.
Sure. Just because it's actually already 5 already, so yeah. I don't know how much time you have, but I'll be here till 6. So we have, going back to this other problem. So this is problem 3 from lesson 21. This is A. And we go down to B. We're over here to C. Above that to D. And then finally to E, where we have another fixed support. Okay, so whenever you have the question written. Oh, you're good. Don't worry. Okay. No, you're good. Okay, so here we have the problem. The dotted line just represents the like standard height of A all the way across. And then we have loads applied at B, C, and D, reactions at A and E. The problem wants us to determine the sag at B and D and the maximum tension in the cable.
Okay.
So we can start off by finding our reactions by doing a couple equations. So what makes this funky is that A and E are not at the same height. So when we do, normally we would just do a moment about one of these points and we'd only have one unknown because they would be in line. Say if we did moment at A, these would both cross off and EX would cross off, we would only have EY. But now if we take moment at A, we're gonna have EY and EX. Same thing if we take moment at E, we're gonna have AX and AY. So what they do is they create multiple diagrams. So what they do first is they say this diagram, moment at E, you set it up by taking all of your forces with their distances and your reactions at A. So you have two unknowns in that equation. So that is going to be moment at E. We'll say clockwise is positive.
So we're finding the reactions, but we're kind of breaking it up in multiple diagrams, you said?
Yeah. So first, I'm just going to write out the equation with two unknowns in it from this diagram. So we'll go clockwise around E of minus 4 kips times 15 feet.
So yeah. So you're saying, well, we'll just skip this.
We'll have minus 12 kips times 30 feet.
Yeah. That's why you said.
And minus 6 kips times 40 feet.
And then we're doing minus AX too, and X.
Yes. And then we get to A, and we'll have plus AY because our moment we said clockwise is going to be positive. So we'll have plus AY times the entire distance to AY. And then we'll have minus AX because AX is going to move this way. As our moment comes around like this, it's going to be moving against AX. So we'll have minus AX times 20 feet. AX is going to be this way. The perpendicular distance is here. So 20 feet. So this equation this will all combine into some number, and we'll have two unknowns, AX and AY. So in order to figure out AX and AY, we can take a cut in our cables.
Okay.
So we can say that if we cut this right here at C, I meant to write that more directly on the C, right through C. We're going to have another diagram. This is A.
Is there any force at C? Is there that?
So we have the 12. We have the 12 kip, and we're also going to have this, which is the cut that we have, that's C and D. So we would say T, C, D here. So then, if we have this diagram, and we do the moment about C, TCD is going to go away, 12 is going to go away. So we'll have another moment equation with the 6, the AY, and the AX, and then we'll have two equations with two unknowns.
Okay.
And that's how we'll solve for AY and AX. So we can do clockwise moment, or some of the moments about C is going to be equal to minus 6.
So when you're not writing equals 0 equals whatever, is that up for a reason? Is that on purpose?
No, I should be writing equals 0.
I just want to make sure. I've been writing equals 0, but I just
Yeah,
want to make sure.
you guys should. I'm just lazy.
Yeah.
So, yeah.
I usually want it, but I was like, oh, is something moving now?
Yeah, no, that's a good question though, because when things do start moving, it's not equal to 0. Yeah, so we'll have the 6 times the distance from C to B, so that's 10 feet. And we'll have plus AY times the distance from C to A, so that's 30 feet. And we'll have plus AX. It's positive now because it's above the moment. And so as we're taking a clockwise moment, spins up like this, that's going to move in the same direction. So the distance to AX is going to be this distance, 5 feet. So this long equation with AY and AX.
Yeah.
Oh, geez, excuse me. Getting like heartburn or like indigestion. We have AY and AX here. So using those equations, we can say that AX is going to be equal to 18 kips to the, there it is, the left, and AY is going to be equal to 5 kips. up. So now that we have these two reactions, we can easily find EY and EX just by doing some of the forces in the X and Y direction.
How did you solve for AY and AX to get to a number?
So we have two equations. So with two equations and two unknowns, you can substitute. So we could say, we can move X over, or AX over, and divide everything by 20 feet. And so this would all combine, these numbers here, get divided by 20, and we would have 3AY after dividing by 20.
Yeah, 3AY equals AX, right?
Right. So we would have all of this plus 3AY equals AX. And then where we have AX here, we can substitute all of that. I can write that out.
Sorry, I don't know why.
No, it's okay. It's okay. So after, I'm going to continue it down here. I'm just going to make sure that the computer can see it. No, don't worry about it, man. There's nobody here. So you would solve this. Let's say, so 4 times 15. What's 4 times 15? 60. So then 12 times 30. Yeah, basically just if you could put this into the calculator, like these numbers here.
So 60. That's 60 right now.
Okay. Did you make sure that all of these were negative? I'm not saying that's wrong. I don't know what the answer is. I'm just.
That last one. Okay.
So this would be minus 4 times 15, minus 12 times 30, minus 6 times 40.
For what you were saying, it's actually pretty helpful.
Negative 660 plus AY. So then I have negative 660, and then that's just before the AY. Negative 660 plus AY is 60.
Okay.
And then
So minus 660 plus 60 AY is equal to 20 AX.
This, then I'm comfortable getting like this.
So then we get negative 33 plus 30 AY equals AX.
Exactly. So now that we have this, we can go back to this equation, and where we have AX, we can put this in instead.
Oh, okay.
So we're just substituting. So we're going to have minus 60 kip foot plus 30 feet AY plus, I'll write it below, plus this quantity, minus 33 plus 30 AY times 5. So where our AX was before, we put this set of numbers in. And so now this equation right here is going to be equal to, to 0, because it's just this. So now we only have one unknown, AY. You distribute your 5, so this would be minus 60 plus 30 AY. 33 times 5 is going to be, so that's minus 165, and plus 150 AY. So that will combine, we're going to have equals to 0, of course. Minus 2 25 plus 180 AY equal to 0. And then your AY is going to be this moved over divided by 180.
Okay, so you don't have to solve for for the first moment. You don't have to solve for AY.
Except
Plug back in. You only need to solve for one.
you only solve for 1, but we messed up somewhere because it's supposed to be 5.
Oh,
So let's see what went wrong.
that's probably my calculations. Yes, I'll track it.
I can check. So the 660 is correct. So it's just this divided by 20, which is 33. This should be 3 and not 30. That's what it is.
Oh, okay.
Because, yeah, 60 divided by 20 is 3, not 30. We had an extra 0. So over here, this is just 3 AY, not 30. So this is going to be 153, which still doesn't make sense. Wait a second. What happened?
Well, okay, so for the moment, we're doing, well, you put negative 60. Okay, oh, you already did that.
This is spiral.
Okay. Plus AY times 30 plus at negative 33 plus 30 AY, right?
Say that again.
So I'm just kind of going back to the beginning when we solved. So we solved
Here?
for, yeah, we solved for AX to get negative 33 plus 30 AY, right?
Yes.
And then we plug that back into the sum of the moments about C, the second equation.
Mm-hmm.
And so we got the 6 times 10 plus AY times 30 plus, and we plug in what we got. So negative 33 plus 30 AY, right?
I believe so. That's.
And we multiplying that by 5 the whole time.
Mm-hmm.
So you do it right there. Doubt I have some sort of answer. I'll try it.
This is 165, not 225. Wait, no, this was 165. Now I'm confusing myself. Again, did I miss something from the diagram? No. All right, this equation is right. So
What did you get finally? Like that you said was incorrect, 1.25?
well, we end up, yeah, so AY is supposed to be 5 kips.
Yeah, I got negative 1.25.
Yeah. Just mentioned calculation. I don't know why.
So he writes this. He has all the same stuff that we do up until the very end part of it, where he says, whoops, he has this, and then this would be minus 60 plus 30 AY plus 5ax, which would reduce to minus 12 plus 6ay plus ax equals 0. Okay, well, I feel like now it's going to work. I think we just like messed up something right at the very end. So if we say minus 12 plus 6ay plus what we have here, minus 33, and plus 3ay. So this is going to be equal to 0. So 33 and 12, that's 45. Move that over. And we have 9. Ay is equal to 45. So I don't know what happened before. We just like,
Oh, that's okay.
something strange happened before.
I thought AY was supposed to be. Oh wait, what is that? Is that 9? Okay.
Yeah.
9 AY.
So ay is what it is. 5 kips. Yeah.
So negative 60 plus 30 AY plus 5 AX, and then
Yeah. So this
yeah,
becomes that over there.
right.
And this, we turn into this.
Oh, so he just reduced.
Yeah, so we reduced all of our, this becomes that. So we reduced all of these terms to be minus 660 in total. And we moved AX over and divided by 20 to isolate it. We took this formula too and did the same thing until we had 12 plus, minus 12 plus 6ay plus ax.
So we just got rid of that 5, so we didn't have to distribute it.
Right. And so when we substitute this quantity for ax here, we get minus 12 plus 6ay minus 33 plus 3ay. That's 3 plus 6, 9ay, and minus 12 minus 33, move it over, that's 45. That's how ay becomes 5.
Okay. I don't know why that's doing.
Yeah, that was, for some reason, it was much harder than it needed to be. Yeah, so that's how you use two equations with two unknowns to solve. And now that we have ay equals 5, we can go back over here and say minus 33 plus 3 times 5 is equal to ax, which is going to be equal to 18. Because this is 15 and minus 33 plus 15 is going to be 18 kips. We get a negative answer, so it's the opposite direction we assumed. That's why it's to the left.
Okay. Got that now. Yeah.
So that's our ax and our ay.
Mm-hmm.
I'm going to erase and just have it ax is equal to 18 kips to the left, and ay is equal to 5 kips up. So now that we found ay and ax, we can do ey and ex by doing some of the forces in the y and x direction. So ex is just going to be equal to ax.
Yeah.
So 18 kips except the opposite direction. So this one will be to the right. And we'll have ey is going to be 5 minus 6 minus 12 minus 4.
Why?
Because when we do some of the forces in the y direction, we're going to have plus ay minus 6 minus 12 minus 4 plus ey.
Oh, okay. I got negative 17.
Okay, so 5 minus all these is negative 17. We move it over, and then it's positive 17. So our direction that we assumed is correct.
Nothing's loading, my guy.
So it's up. And we have all of our reactions now. So now we can actually answer the question, which is determine the sag at B and D and the max tension.
Okay.
So in order to find the sag at B, we can take essentially a cut right here. And I'm just going to use this same diagram. I'm just going to erase this and call this one here TBC. Do you see where this came from?
Mm-hmm.
Okay. So once we have that, in order to find the distance, I see. They do the moment at B, because when we take the moment at B, TBC is going to go away, this 6 is going to go away. We're only going to have AX and AY, except the unknown we're looking for is this distance.
Okay.
We already have the distance here, and the distance here is the sag at B.
Okay.
So this I'm going to say is YB. So we'll do the moment at A is equal to 0, is equal to values we've already found, AX and AY. So AY is going to be plus because it goes this way.
Plus 18.
Yeah, so plus 18 times the distance here from A to B, 20 feet. And then we'll have, we know that AX is going to the left, so I'll change this. So that will be negative because it goes against the clockwise moment. We'll have minus, this was supposed to be 5. Because this is AY. Yeah, this is AY, and this is 20. And so the AX, 18, is going to be multiplied by our YB, this distance. And so then we just say the YB is equal to 100 divided by 18. So 5.6 for the sake of it, feet. And that's the sag at B, first part done. Then we need the sag at D. We can do the same thing that we just did, but on the other side. We can go from here, from point E to D, where, not B, sorry, to D, where we have the 4 kips. And TDC.
Why are you writing T there? Is that tension?
So yeah, the T's are the tension forces. So when we take this piece of it, you just treat it like it's a structure made of members, and wherever you take a cut, you're gonna have an internal force. In this case, it's tension. We're just assuming tension. So this is tension through DC, and we can do the same thing we just did, where we have EY and EX. And we know this distance. And we want to find this distance. This is going to be our YD. So moment at D, just like we did before, is equal to 0. That's D. It's going to be equal to, this goes away, this goes away. We're going to have minus EY, because EY is going to move against our moment. And EY is 17, so we'll have minus 17 times that distance from D to E of 15 feet. And we'll have plus EX, which is 18, times YD, what we're looking for. So YD is going to be equal to 17 times 15 divided by 18.
14.16.
14.16 feet. And I believe that we just found, yeah, that's what I thought. So we haven't found the sag of D yet. So we found the distance from E to D. The sag of D is the distance from the center line to D. Whereas before, when we did B, the distance we calculated from A to B was already the distance from the center line to B. And so now we calculated from E to D. So the sag is going to be this portion, 20 minus what we found. So sag B was equal to 5.6. And sag D is going to be equal to 20 minus 14.16.
What is it?
So the sag at D is going to be this distance.
Yeah.
So it's 20 minus what we just found for this distance.
$5.4.
5.4, which is, wait, what? 20 minus 14.16. 5.84. Oh, I didn't hear the 8.
No, I didn't actually say that.
Oh. That's my bad.
I put 14.6 in at first. Sorry.
I see. No worries. No worries. Always double check your calculator work. Always. It's worth it. Those are our two sag values. We've now can check that off. Check that off. We now just need the max tension. Okay, so they say that the max tension is going to be in the when we look at the free, like the whole free body diagram. So we'll have our AX and our AY as reaction here, and EY and EX as our reaction here. We need to do, oh, okay. I totally was confused by what they were doing because we already found EX and EY and they were doing it just now in the solution.
Oh, okay.
But so we've already done the part of finding EX and EY. So, but now that we have that, the max tension is going to be either at AB or ED. And we can pick the proper one by looking at which point has the higher reaction values. And so our E values are higher. And so we say that T max is equal to the sum of these squared, and square root that.
Okay, so how can we find which ones to choose from?
So the one you pick, we want to find the maximum tension. So we're going to pick the support between A and E, whichever one has the higher reaction values, because that will generate a higher tension. Mm-hmm.
Take the higher reaction. Okay. So
Mm-hmm.
T
Is going to be our X and Y component.
okay.
I believe in you.
$24.76.
They say 24.8, but I don't know how that would be.
Yeah, it's 758, so 24.8. Yeah.
Okay, yeah. 24.8 kips. And that would be your T max. So the thing about this problem, like this specific example, is that like it looks like there's a lot going on here. But in reality, the hard part is just like the hard part is not messing up the numbers.
Yeah.
Because all you got to do is find the reactions with the moment setup that we went over before, where you do moment at one point, and then you get one equation, then you do moment at a cut, and you get the other equation. And we just like mess that up super bad somehow in this problem.
So he just did a cut. He did one. Why did you do two cuts both below the horizontal line? So like to me, I mean, I don't know. At like a cut like C and a cut at D.
A cut at C and a cut at D.
Yeah, like how come we did two both below the line?
Oh, so I did the cut at B first to get the second equation for our A values. Okay. So initially I did the moment at E to get one equation with both of these unknowns. And then if we take a cut at B and we do the moment at B, this tension force will go away, this force will go away, and we'll only have these as our unknowns.
Okay.
And that's where we got two equations for two unknowns.
Yeah. Okay. And then cut at C.
And then, yeah, we cut it. Sorry, we cut it at C to get the second equation for these. We cut it at C to get the second equation for these because we know this distance. Yeah, we couldn't use B because we didn't know this distance yet. But we did our first equation for AX and AY by doing the whole diagram, moment at E. And then we took a cut at C, got the second equation for AX and AY. Then once we found those, we could find EX and EY. And then finally we can do a cut at B and a cut at D. I'm gonna write this here too, like this. Those two cuts at B and D let us take just this piece and just that piece, and you can do a moment here with two knowns to actually solve for distance instead of force like you usually would. Same thing for here. We took the moment here, got rid of these, and then with these being known, we can solve for distance.
Okay.
And then
distance by finding that YD created we kind of just created a moment there or a tension there to find that.
Yes.
Use it as finding distance. Okay.
Mm-hmm. And then the sag that it actually wants is the distance from the center line, which is where it begins, to that point. So for B, it was the value we got right away. And for D, we had to do 20 minus the value we got since we took D from E.
Right.
So the actual sag was down here. So I guess for these, I don't know if he wants to specify a distance, but you would say 5.6 feet down, and you could say 5.84 feet up. And then Tmax is just the reaction that you have that has the higher values. And if they're weird, like if one of them's like 4 and 27 and the other one's like 2 and 50, and you're like, I don't really know, just test them both, and whichever one's higher is the one you pick.
Okay. So like, or whichever one is like, would it matter too, like if you found the distance between the sags of both, whichever one is the higher sag, that one you're subtracting? So like since sag D was 5.84 compared to 5.6, we subtracted that one from 20.
Oh no, so we subtract from 20 because the value we got in this moment equation for this distance from E to D was 14.16, but the actual sag is the distance from this line to D. So it's going to be 20 minus this.
Oh, you're right. Okay.
Yeah, so the max is just going to be like, no matter what these numbers are, you can just test both of them, A and E, and whichever one is higher is your max.
Okay.
But usually you should be able to tell based on what your components are, where it's like, okay, the E ones are obviously higher because these are the same, and EY is greater than AY.
Okay.
So that's how you would know which reaction values to use to get your Tmax.
Yeah. Okay. Could you not just do like, you got like a 4 and 30 and like a 1 and 50? Could you not just subtract them to see which one's greater and then use those?
You wouldn't have to subtract them. You could just do, like, if this was some arbitrary numbers and these were some arbitrary numbers, but you couldn't really tell which ones would give you the bigger one, you would just do square root of sum of the squares of these and square root of sum of the squares of these, and whichever one is bigger, then that's your answer.
Okay.
And that is cables. So cables are a lot like trusses and things like that. You can treat a cable like it's a two-force member.
Okay.
Mm-hmm.
Okay.
So whenever you cut it, it's going to generate a tension value, but you can cut it to like make the diagram different.
Yeah.
And that's how you can get extra equations that you will probably need to solve the problem.
Right. Okay. Okay. I think I got it.
All right. Any questions?
I don't think so. I'm probably gonna go through and try to see other ones too, and kind of look through them. And
Okay.
Kind of go back to these and see like similarities in all of them.
All right.
Just find out like the process.
And your quiz isn't until Monday, right?
Yeah, it's Monday.
Okay. So if you have any questions over the weekend, just shoot me an email and I'll get back to you whenever I get it.
Yeah, I will. Awesome. Okay. Thank you.
No problem, man.
Are you gonna be here till 6? Just kind of hanging out?
Yes, I'll be here for like 10 more minutes. Yeah, it's already 5:50. Yep. But that's what I signed up for, so.
So you have to keep the Zoom up in case anyone comes in.
Yeah, I've been keeping an eye on it, but since people left earlier, nobody else has came. But you know,
Guess they know everything.
I guess that, or they think they do, or they hear me say that I'm going to upload it,
Oh, yeah.
and they're like, "All right, I'm out." But what sucks is when everyone does that, there are less questions getting asked, and so the video like is not as good as it could be if people were here.
Yeah.
Like more people being like, "Oh, hey, this other question that other people probably have," you know. But I try to like be as thorough with the process as I can.
Even without like people asking.
Mhm.
Yeah.
That's why I always like will reiterate over and over again, like, oh, it's equal to 0 because nothing's moving, and oh, it's plus or minus based on the direction of the moment that we take. And so those kinds of things are like the little mistakes that will lose you points.
That's it's just like remembering
Mhm.
from like fast as it goes.
Yeah.
A little we have to do it.
Yeah.
Yeah.
Hmm.
All right, thank you.
No problem, man.
Yeah, I might have to treat you.
Awesome. You too, dude.
Yeah, no, mine's gonna process. Yo, Noah.